This comes out of section 7.4, applications of trig derivatives. It says two sides, yikes, spelled two wrong, that's good. Two sides of a triangle have lengths 12 centimeters and 18 centimeters. The angle between them is increasing at pi over 50 radians per second. How fast is the length of the third side changing when the angle between them is 2 pi over 3? So we have two sides, if you can picture this, two sides, one's longer than the other. And this is the angle we're talking about, and this is the third side we're talking about. This side stays at 12, and this side stays at 18, which means we're definitely not talking about strictly a right-angled triangle. So we can't use our regular SOHCAHTOA or Pythagoras or anything like that. I would likely give you, or the book or somebody would give you, if they were asking you this question, the cosine law, which is a squared equals b squared plus c squared minus 2bc cos A. It's basically a modified version of Pythagoras that includes triangles that aren't right-angled triangles. Now in this case, if I call this side, I suppose, x, and my angle theta, I've got x squared equals 12 squared plus 18 squared minus 2 times 12 times 18 times cosine of theta. So I have, two unknown things here in this equation. I have two variables. I have x and I have theta. If I take that a step further before bothering to take, I won't take the derivative just yet. I'll have x squared equals, if I do some of this number crunching here, 468 minus 432 cos theta. So at least I have, I know d theta by dt from what was given in the question, and I want dx by dt. That's a perfect situation, because now I'm going to differentiate everything with respect to time. So I will get 2x dx by dt equals 0 minus 432 times negative sine theta d theta by dt. So the derivative turns out not to be that terrible, and in fact these negatives even cancel out, and I say, well, dx by dt then equals, I'm going to divide by 2x, so I'm going to divide that by 2, which would be 216 sine theta over x d theta by dt. Now, they told me right in the question d theta by dt is pi over 50. They told me right in the question that theta is 2 pi over 3. The one thing they didn't tell me in the question was x, but I can, at the instant when theta equals 2 pi over 3, I should be able to, I know about 2 pi over 3, it's a 120 degree angle. I know that I should be able to use this cosine law above and say, well, x squared is going to be 468 minus 432 times cosine of 2 pi over 3. Cosine of 2 pi over 3 happens to be negative 0.5. And so if that's the case, I end up with x equals the square root of 684, or if you prefer 6 root 19. So at this instance, so we've got dx by dt equals 216 times sine of 2 pi over 3 divided by 6 root 19 times pi over 50. Now that's a lot of exact value stuff to keep track of, but nothing too unmanageable. Sine of 2 pi over 3 happens to be root 3 over 2, nice unit circle number. And if you crunch all this, you're going to get one of a couple things. You might start off getting reducing the fraction. You got 9 times pi root 3 over 25 root 19. I got that at some point. If I rationalize it, I've got 9 pi root 57 over 475. Or if you just give up on exact values completely, you'll end up with about 0.45 as your answer. And looking back at what the units would make sense here, we were dealing with centimeters and we were dealing with seconds. So if this angle in this triangle is growing at pi over 50 radians per second, the side itself that's missing there is growing at 0.45 centimeters per second. Nice example of a related rates question having to do with trigonometry.